Imagine you are monitoring a massive, complex, autonomous infrastructure. You were just sitting there looking at your dashboards, watching the telemetry flow by.
Waiting for something to go wrong, basically.
Right. You're braced for a failure. But the scariest alert you can get in that environment isn't a red flashing light.
No, definitely not.
It's not a glaring error message, and it is certainly not a crash report. The most terrifying thing you can see is actually the green check mark.
Oh, absolutely.
It's that standard web response, right? The 200 OK that tells you a job completed perfectly. But the actual physical outcome you desperately needed, whether that is a process file or a transferred data set, is just completely missing.
It's a terrifying paradox. And, it goes against every instinct we have as engineers and operators.
Because we love the green check mark.
Exactly. We have been conditioned for decades to seek it out. I mean, in traditional computing, if you get a 200 OK or standard Unix exit code of 0, you just breathe a sigh of relief. The system worked.
The pipeline is healthy.
Right. But we are moving into an era where that assumption is fundamentally broken. We are confusing a transport success with a verified outcome.
Which are two vastly different things.
It's vastly different. And in the world of autonomous agents, that confusion isn't just like a minor bug. It is a catastrophic vulnerability. A perfectly successful process exit can seamlessly, happily coexist with absolutely missing work.
And you're about to explore exactly why that is the most dangerous failure mode in autonomous systems today. Welcome to this deep dive, which we are calling the agent that says 200 OK.
It's a great title.
Thanks. Today, our mission is to completely unpack how we verify that AI agents are actually doing their jobs rather than just politely telling us they did.
Yeah, the politeness is the dangerous part.
It really is. So we have a fascinating stack of sources guiding our discussion today, and we're going to weave them all together. We are pulling from a highly curated internal source packet, a recent Twitter intelligence scan, some very sharp editorial angles from the Social Scout feeds, and a set of local pipeline recovery records.
Which give us a literal front row seat to the problem.
Exactly. Okay, let's unpack this carefully, because the history of why systems behave this way is just as important as the modern consequence.
It really is. I mean, to understand why an agent can fail while reporting success, we have to look at the architecture it sits on top of.
The internet itself, basically.
Yeah, the 200 OK status comes from HTTP, right?
Yeah.
The protocol that runs the web. When HTTP was designed, it was built for document retrieval.
You asked a server for a web page, and it handed it back.
Right. The server's only job was transport. It didn't read the document to see if the information inside it was factually correct.
Or if it looked pretty.
Exactly, or if it made logical sense. It just looked at its hard drive, found the file, and shipped it over the network. So the 200 OK simply meant, I successfully heard your request, I found the payload, and I handed it to the network layer.
It is an infrastructure fact.
Yes. It is not, and never was, an editorial fact.
So the system is basically acting like a mail carrier. I mean, the mail carrier's job is just to put the envelope in your mailbox. Right. They don't open the envelope to check if the letter inside actually says what it is supposed to say, or, if the check inside is signed. If they drop the envelope in the box, their job is 100% successful.
Precisely. And for decades, that was fine. Because humans were the ones opening the envelope.
You were the quality control.
Right. The human provided the semantic verification. The computer just provided the transport. But now we are building pipelines where the sender is an automated script, the transport is an automated network, and the receiver is an autonomous AI agent.
There's no human in the loop to open the envelope and say, wait a minute, this is blank.
Exactly. The human is entirely removed from that verification step.
Let's make this incredibly concrete for you listening right now. We have a local pipeline recovery record in our internal source packet that perfectly illustrates this dynamic in the real world.
This is a great example.
Yeah, so imagine an automated scheduler within a media processing company. Its job is very simple. Fire off a specific script every hour on the hour. So the clock strikes, the scheduler fires the script. A fraction of a second later, the scheduler records an OK status.
Green check mark. Everything looks fantastic on the central dashboard.
And if you are the on-call engineer looking at that dashboard, you just go back to drinking your coffee. You assume the hour's work is done.
Because the system told you it was.
Exactly. But here is what actually happened in the dark, underneath that green check mark. The script woke up, and it looked around for its expected input. Let's say it was looking for a specific creative brief, or maybe a raw audio file that an agent was supposed to summarize.
But because an earlier step in the pipeline lagged, That file was absent.
It just wasn't in the folder. So the script, following its basic rudimentary logic, decided, well, the input folder is empty, therefore there is nothing for me to do here.
And it politely exited with a success code?
Right. It didn't crash, it didn't throw an exception, it just successfully did nothing.
What's fascinating here is how the logic of the system turns a completely logical micro decision into a macro-level failure.
Because the code did exactly what it was written to do.
Right. The scriptwriter probably thought they were being responsible. They wrote logic that essentially says, if input equals null, exit cleanly. They didn't want the script to crash and throw a massive error just because a file was a few seconds late.
But by exiting cleanly, the script tells the scheduler, I completed my run without error.
Yeah, it's the delivery notification problem.
Oh, it's exactly like receiving a delivery confirmation email from a courier company. You get the little chime on your phone, you open the email, and it says, delivery successful, with a bright green check mark.
But the package was never even loaded onto the delivery truck at the warehouse.
Right. The email system, the notification layer, worked flawlessly. The transport of the message was a complete success. But the physical reality of the transaction, the actual movement of freight, is an absolute failure.
You still don't have your package.
But the system is entirely convinced you do.
That analogy hits the core of the issue perfectly. The notification system is entirely decoupled from the physical reality of the freight. And, when we apply this to automated software pipelines, the operational fix is quite clear.
Though it's chronically ignored by development teams, right?
Highly ignored. If a script requires a specific input to perform its value creation job, and that input is missing, that scenario should never, under any circumstances, result in an OK status.
It has to trigger an error.
It must trigger a non-zero exit status.
But if I play devil's advocate for a second here, if I'm an engineer, I don't want my pager going off at 3 a.m. just because a file was 30 seconds late.
Of course not.
So if I trigger an error every time an input folder is empty, I'm going to have like 1,000 false alarms a day. Isn't that why they program it to exit cleanly in the first place?
It is the exact reason they do it.
Right.
And it highlights the tension between operational silence and operational truth. Engineers optimize for silence.
They just want to sleep.
Right. They want the dashboard to be green unless the server is literally on fire. But in an autonomous pipeline, silence is deadly. The fix isn't to just throw generic errors, though.
What is it then?
It is to create highly specific, nuanced states. An automated release gate must be able to distinguish between two very different realities. State A is, I checked for new work, there is nothing new to process at this time, so we are in a verified, expected, steady state.
Okay, that's fine.
Right. But state B is, I was explicitly instructed by the scheduler to process a specific brief, and I could not find that specific work.
So it's the difference between I am on patrol and the neighborhood is quiet versus I was told to go to 123 Main Street to stop a burglary, and a 123 Main Street doesn't exist.
Exactly. The former is the peaceful, steady state. The latter is a critical failure in the instruction chain. And right now, in most architectures, those two completely divergent realities are wearing the exact same green camouflage.
The system literally cannot tell the difference.
It has no idea.
And this infrastructure quirk, which, let's be honest, used to just cause a minor headache for a data engineer who had to manually rerun a cron job on a Tuesday morning.
Yeah, an annoyance, really.
Right. It becomes a completely different beast today. It becomes a massive company-ending security and operational liability once we start letting AI agents cross trust boundaries.
Oh, absolutely.
Because it is one thing if a dumb Python script fails to move a text file. It is another thing entirely when an autonomous agent has the keys to the kingdom and it thinks it's successfully executed a security patch when it actually did nothing.
That is the critical pivot point. We are moving from a paradigm where models just answer questions, where they are essentially just advanced conversational encyclopedias.
Or a fancy calculator.
Right. We're moving from that to a paradigm where agents are handling actual execution. They aren't just drafting an email for you to review anymore.
They're sending it.
They're reasoning through multi-step problems. They are autonomously calling external tools and APIs. And most critically, they are touching credentials.
They are crossing the trust boundary from passive advisor to active actor.
Yes.
Let's define what we mean by trust boundary, actually, because that term gets thrown around a lot. To me, it implies a line where the consequences of a mistake go from embarrassing to destructive.
That is a very practical way to look at it. Technically, a trust boundary is any place in a system where data or execution changes its level of trust. So your public-facing web server is on one side of a trust boundary.
Because it's exposed to the internet.
Exactly. So it is inherently untrusted, but your internal customer database is on the other side. It is highly trusted.
Yeah.
When an AI agent moves from simply summarizing a public Wikipedia article to querying your internal database to build a report, it crosses that boundary. It now requires authorization, authentication, and a verifiable chain of custody for its actions.
Which brings us directly to some very striking data from our Twitter intelligence scan. You're looking at a stream of operational intelligence, and the scan surfaced an attributed social post from the cybersecurity vendor Sophos.
Right, I saw this one.
Yeah. They were looking at a sample of blocked agent-like activity on corporate networks, and they noted that 56.2% of this blocked activity involved credential access, and 28.8% involved code execution.
Which is wild.
Think about that for a second. Over half of the blocked autonomous behavior they were observing was an entity actively trying to get its hands on passwords, API keys, or access tokens.
I need to step in right here, though, because as analysts, we have to put a massive heavy guardrail around those numbers for our listener.
That's fair. Go ahead.
It is absolutely crucial that we treat this only as one specific vendor's attributed observation from a social media post. This is not a universal industry benchmark.
It's not a global statistic.
No, it is not a generalized, scientifically peer-reviewed rate of all AI agent behavior across the entire internet. Our source pack explicitly notes there is no linked primary report for these figures. We must view this strictly as a localized snapshot.
Just one data point from one vantage point in a very specific context.
Exactly, not as an undisputed empirical law.
That is a really important distinction, and I'm glad you brought that up. We aren't sitting here saying the whole world is experiencing exactly 56.2% credential access attacks from rogue AIs today.
Right.
But even as a localized snapshot, even as just a directional indicator from one vendor's telemetry, it forces a very serious conversation because it perfectly illustrates the type of battlefield we are walking onto when we give agents autonomy.
It absolutely does. The core utility of that Sophos observation, regardless of the exact percentage, is that it highlights a fundamental systemic security crisis we are about to face.
Which is what?
That ordinary, traditional behavioral detection systems are going to struggle immensely to distinguish between a legitimate AI coding agent going about its authorized business and an adversary attempting to breach the system.
Let's dig into that mechanism. Why is that distinction so hard for the system to make? I mean, aren't security tools designed to look for bad behavior?
They are, but they look for bad behavior by searching for anomalies actions that deviate from the baseline of a normal human user. So imagine a traditional endpoint detection and response system.
An EDR.
Right, an EDR. It sits on a computer and watches what happens. If a human in the marketing department suddenly opens a command prompt, runs a PowerShell script, and tries to read the memory space where passwords are kept, the EDR flags it immediately.
Because marketing people don't do that.
Exactly. It is highly anomalous.
Right, that looks exactly like a hacker trying to steal credentials.
Precisely. But now, imagine you deploy a legitimate, authorized AI agent whose specific job is to help the DevOps team manage infrastructure.
Okay.
That agent's literal job description is to wake up, write a script, access a database, retrieve an API key to authenticate itself, and deploy an update. If you look at the behavioral signature of that legitimate agent,
it looks almost identical to the malicious threat actor trying to execute code and steal data.
It really does. The keystrokes, the API calls, the memory reads, the physical actions are the exact same. The intent is the only differentiator.
And intent is completely invisible to a network monitor.
Completely invisible.
So the security system is looking at the agent and saying, well, you are running code and grabbing passwords, which is exactly what a hacker does. But you also have a badge that says DevOps Helper AI. I have no idea if you're doing your job or if you've gone rogue.
Exactly. And this is exactly why the new stack, which was also captured in our Twitter intelligence scan, presented such a fascinating counterpoint to the idea that AI will just replace human oversight.
Right, the human element.
They argue that as AI agents handle more of this raw, complex execution, human purpose doesn't become obsolete. It doesn't fade into the background. It actually becomes more important, just in a completely different capacity.
Because we have to set the rules.
Yes. Humans aren't just sitting at the end of the assembly line proofreading final outputs anymore. They're the ones who have to define the boundary around action itself.
I love this framing because it shifts the human from a micromanager to an architect. If we connect this to the bigger picture, you are no longer telling the computer how to do the task.
Right.
You aren't writing the step-by-step code. You are defining the exact perimeter of what the computer is authorized to touch while it figures out the task itself.
Right.
You are drawing the blast radius.
Drawing the blast radius is the perfect way to visualize it. You are telling the system, the agent is allowed to read from this specific database table, it is allowed to write to this specific temporary folder, and it is allowed to spend up to $50 on this cloud API.
And if it steps outside
You tell it, if it tries to touch anything outside that box, kill the process instantly. The human defines the perimeter. The agent figures out the path within it.
But enforcing that boundary creates a completely new problem. If we lock down what an agent can touch and we rely on it to act autonomously inside that box, how do we measure if it's actually making good decisions?
That is the million-dollar question.
Right. Like, how do we know the agent isn't just confidently marching in the completely wrong direction, doing the wrong work, but doing it perfectly within the rules we set?
And this is where the industry is currently stumbling. Because right now, developers are utterly obsessed with confidence scores.
Oh, yeah.
You ask a large language model or an AI agent to do something, it processes the request, and it comes back and says, I am 99.9% confident in this result. It gives you a mathematical assurance of its own brilliance.
We pulled two very striking editorial angles from Social Scout that hit right at the heart of this. The first angle is this exact phrase, a confidence score is not provenance.
Such a good quote.
And the second one, running right alongside it, is agent consensus doesn't mean correctness. So let me process this aloud. If an advanced LLM built by the smartest engineers in the world gives me a 99% confidence score on a decision it just made, why shouldn't I trust it?
I mean, it sounds trustworthy.
Right. Isn't a high confidence score basically a guarantee of quality?
It feels like a guarantee, but to understand why it isn't, we have to look under the hood at how these models actually generate that score. Large language models, at their core, are next token predictors.
They're just guessing the next word.
They are highly sophisticated statistical engines that calculate the probability of the next word or token in a sequence. When an LLM says it is 99% confident, it is not expressing epistemological certainty about a fact in the real world.
It doesn't actually know anything.
No. It is simply saying, based on my training weights, the statistical probability that these specific words should follow each other in this specific syntactic order is 99%.
So it's highly confident in its grammar, not necessarily in its reality. It's like someone speaking with absolute unwavering conviction and perfect elocution, but the words coming out of their mouths are complete fiction.
Yes. It can be highly confident simply because it recognizes a familiar syntactic pattern. It is pattern matching, completely divorced from factual reality. Like, if you ask it to write a biography of a fictional historical figure, but you frame it using the exact structure of a real historical text, the model might be incredibly confident in its output because the structure matches its training data perfectly. The confidence score is a measure of statistical alignment, not a measure of truth.
Okay, that makes sense for a single agent hallucinating. But let's look at the second Social Scout angle. Agent consensus doesn't mean correctness.
This one is huge.
If I know one agent might hallucinate, the logical engineering fix is redundancy, right? If I spin up 5 different agents, give them the same task, and all 5 of them independently agree on the exact same action, shouldn't I trust that consensus?
You'd think so.
If 5 different systems point the same way, the odds of them all hallucinating the exact same thing have to be astronomical.
It is incredibly tempting to trust that because human intuition tells us that a crowd is wiser than an individual. But in AI, this leads directly into what we call the consensus trap.
The consensus trap.
Yeah. Repeated agreement among autonomous agents can simply mean they are repeating the exact same blind spot. This phenomenon is known in the field as correlated consensus.
Break that down for me. What causes correlated consensus?
It happens because these agents do not exist in vacuums. If you have 5 different agents, but they were all fine-tuned on the same underlying foundational data set, they share the same biases.
Ah.
If they all use the same web scraping tool to research a problem, they will all read the exact same flawed article. If they all reference the same stale memory cache within your corporate network, they are all looking at the same outdated fact.
So they aren't actually independent?
Not at all. Their agreement doesn't compound into a deeper truth, it just amplifies the original error. They are copying the same bad input. It is an echo chamber of algorithms.
So to use an analogy, it's not like asking 5 different experts for their independent opinions. It's like having 5 students taking a test. If they all secretly copy off the exact same kid in the front row, and that kid studied the wrong textbook, the teacher's going to get 5 identical wrong answers.
That is a brilliant way to frame it.
The consensus doesn't mean the answer is right. It just proves they all share the exact same bad source material.
Exactly. The fact that 5 students gave the same answer gives the teacher a false sense of security, just like 5 agents agreeing gives a developer a false sense of security. And this brings us back to the distinction between confidence and provenance.
Right, the first social scout angle.
Yeah. A confidence score tells you how strongly the student believes their answer. Provenance tells you why they believe it. Provenance is the bedrock. It is the citations, the logic chain, the exact state of the data at the moment the decision was made.
Is the student showing their work on the test paper step by step?
Yes.
Okay, so are we saying we should just throw confidence scores in the trash entirely? Should developers strip them out of their dashboards? Because it seems like we're throwing away a potentially useful signal just because it has flaws.
No, we absolutely do not ban confidence scores. They are practically useful, particularly for ranking human attention and triage. Well, if you are an operator staring at 10,000 alerts, you might want to look at the ones the system is most confident about first to clear the easy stuff. Or, conversely, you might want to look at the ones it is least confident about, because those represent edge cases where the AI is confused and needs human help.
Yeah.
The scores are useful for sorting the pile.
Right, they are a prioritization metric, not a truth metric.
Exactly. But the critical middle ground, the non-negotiable rule for autonomous systems, is that a confidence score must be paired with a compact, verifiable evidence receipt.
A receipt.
Yes, you cannot just accept an agent saying, I am 99% sure we should delete this database. You must demand, I am 99% sure we should delete this database. And here's the exact cryptographic hash of the policy document that authorizes it.
Oh, wow.
Here's the timestamp of when I read that document, and here's the specific secondary tool I use to verify that the database is actually empty.
Just so we're absolutely clear on the terminology for everyone listening, when we say cryptographic hash in this context, we're basically talking about a unique digital fingerprint for that exact version of the document, right?
Correct.
So if a single comma changes in the policy, the hash changes, and we know the agent's looking at the wrong version.
Precisely. It is a mathematical proof of the data's exact state. It removes ambiguity entirely.
So what does this all mean?
Yeah.
We have established that we need provenance, we need evidence receipts, and we can't just trust a green check mark or a high confidence score.
Right.
How do we actually build these evidence receipts in practice? How do we engineer a system that enforces this? Because it sounds like we need to stop looking at chatbot architectures, which are built for conversational fluidity, and start looking at systems that are already incredibly paranoid about state changes.
That is exactly where we have to look for inspiration. We need to look at systems where a failure in state management doesn't just mean a funny hallucination, but has immediate, catastrophic, irreversible consequences.
Like financial systems.
We need to look at financial ledgers. And that brings us to the concept of the settlement layer.
Okay, I want to pause right here and put a massive disclaimer on this for you, the listener. We are about to mention Bitcoin.
Please listen to this disclaimer.
Yes. We are not advocating that you need to put your AI agents on the blockchain. Please do not walk away from this deep dive thinking you need to invent a new cryptocurrency token or burn massive amounts of energy or set up a decentralized node network just to run a customer service AI.
That would be a nightmare.
We are looking at Bitcoin purely as a philosophical lens. We are borrowing its core architectural lesson, which is this. Consequential state changes need hard evidence and clear authority.
I am very glad you clarified that. If we connect this to the bigger picture, the genius of the Bitcoin ledger for our specific purposes here isn't the decentralized mining network, it's the absolute uncompromising requirement for settlement.
Explain settlement.
When a transaction occurs on that ledger, there is no ambiguity. The state of the system changes from state A to state B, and that change is cryptographically proven, explicitly authorized by a private key, and completely immutable.
You can't undo it.
No. When we translate this philosophy to AI agent workflows, it strips away all the sci-fi magic of artificial intelligence and leaves us with boring, necessary, fundamental engineering controls.
And boring is exactly what we want when an autonomous system is touching our infrastructure.
Definitely.
So what are those fundamental controls? What does a settlement layer for an AI agent actually look like?
It breaks down into 4 core mechanical requirements. First, you need bounded permissions, which we discussed earlier with the blast radius.
Right.
Second, you need durable artifacts that prove what happened, the receipt we just talked about. Third, you need checksums, like the cryptographic hashes, to verify that the data integrity hasn't drifted between steps.
Okay, and the fourth?
And fourth, and perhaps most importantly when dealing with autonomous systems, you need idempotency.
Let's define idempotency and really dig into it, because it's a word that gets thrown around in engineering meetings, but it is the absolute linchpin here.
It really is.
The best real-world example of idempotency is an elevator button. If you walk into a lobby, walk up to the elevator bank, and press the up button, the button lights up, the system registers the request, and an elevator is summoned to your floor.
Right.
Now, if you are impatient and you stand there mashing that button 10 more times, you do not get 10 elevators showing up.
No, you don't, because the elevator control system is idempotent. It recognizes the desired end state. A user wants to go up from the lobby.
It absorbs the extra inputs.
Once that state is registered, repeating the exact same action, pressing the button again, yields the exact same safe state without duplicating the consequence. The system absorbs the repeated inputs without compounding the physical action.
Now let's take that concept and apply it to an AI agent. Let's say you have an agent authorized to interact with your cloud provider's API. Its job is to spin up a new server when traffic spikes. The agent sees a spike, decides it needs a server, and fires the execution command. But then there's a network stutter. The agent doesn't get a response right away, it gets confused. So its internal retry logic kicks in, and it fires the command again, and again, and again.
If your infrastructure interface is not strictly idempotent, you didn't just spin up one server, you just bought 10 servers.
Oh, man.
Or if it's a financial agent, you just wired a vendor payment 10 times. Or if it's a legal compliance agent, you just sent 10 identical breach notification emails to a regulator.
Which is a disaster.
For an agent that is authorized to touch side effects in the real world, the architecture must guarantee that repeating a command safely resolves to the same intended state without triggering a cascading disaster.
And this ties directly into another fascinating editorial angle we pulled from Social Scout. The quote is, "Trainable skills don't compound. Stable interfaces do."
This is such a critical insight.
Right now, the entire AI industry is obsessed with skills. We're all trying to teach models new tricks, make them smarter, increase their context windows so they can remember more, and make them more adaptable to weird edge cases.
Yeah, everyone wants a smarter model.
But this angle suggests that adaptability, the very thing we praise in AI, is actually the enemy of reliability when you are trying to settle a state change.
It is a profound observation, but we need to add some specific nuance to it. Interfaces do not magically remove model drift. A large language model will always drift over time.
When you say model drift, break that down for the listener. Why does a model change if the code doesn't?
Because the model isn't static code, it's a massive matrix of probabilities. Model drift happens as the underlying weights are updated by the provider, or even more commonly in a single session, as its context window fills up.
The context window being its short-term memory for that specific conversation or task, right?
Yeah, exactly. Imagine an agent reading a massive textbook. As it reads chapter after chapter, its short-term memory gets crowded. By chapter 20, it might start forgetting the exact instructions it was given in chapter 1.
It gets lost in the weeds.
It starts hallucinating details, or it gets distracted by a tangent it read in chapter 10. Its behavior drifts from the original instruction. Now, you cannot prevent an LLM from doing this. It is the nature of the technology.
Okay, so what do we do?
What a stable interface does is make that drift observable.
So if the model's brain is naturally going to wander, the interface acts like a guardrail that instantly snaps it back, or at least alerts us that it has wandered.
Yes. If you have a strict, unchanging, rigid contract for how an agent must report its actions, a very specific format for the inputs it received and the outputs it generated, you can instantly detect when the agent starts acting erratically.
You can catch it in the act.
A stable interface allows for containment. It gives you a rigid mathematical yardstick to measure a highly fluid, probabilistic intelligence.
It's the difference between asking an agent to go be helpful, analyze these files, and write me a nice summary of what you did, versus saying, you must fill out this exact standardized form with your results, putting the file name in box A, the word count in box B, and the summary in box C.
Exactly.
The form doesn't physically stop the agent's brain from going crazy, but if the agent loses its mind and starts writing a poem about the ocean in the tax ID field, the system instantly knows there is a problem.
Precisely. The rigid interface allows the automated release gate we talked about earlier to actually function. It allows the system to definitively say, I am halting this workflow right now, not because the agent failed to respond, but because the agent's response structurally violates our contract.
That makes total sense.
It turns a semantic failure into a syntactic failure, which a computer can catch instantly.
Okay, this is a great philosophical discussion. The theory of the settlement layer, the idempotency, the rigid interfaces, it all sounds incredibly sound. I'm nodding along, you're nodding along. But how do you, the listener, actually implement this today? We need to move from the abstract philosophy of settlement to a concrete operational checklist. We need a way to replace the vibes and the long, rambling chat transcripts with actionable receipts.
And this is exactly where the rubber meets the road. Another Social Scout angle hits this operational reality perfectly. Agent handoffs need a receipt, not a chat transcript.
Let's unpack the difference there. Because right now, a lot of agent frameworks just pass the entire chat history from agent A to agent B. Why is that bad?
Because a chat transcript is unstructured narrative. It is essentially a novel that the AI wrote about its own day.
And computers hate novels.
A machine cannot easily parse 100 lines of conversational text to determine if a critical security check was bypassed or if a specific file was definitively verified. It requires another AI to read the transcript and guess what happened, which just introduces more probability of error.
So what's the alternative?
We need a pragmatic, deterministic 5-question handoff checklist. Before an agent workflow can proceed to the next step, before it hands off its work to another agent or a human, it must comprehensively, structurally answer these 5 questions.
Let's go through them one by one. Question 1.
First, what input did the agent actually receive? This sounds incredibly basic, almost insulting to ask, but it is the foundation of trust. We cannot just assume the agent saw the document we intended it to see.
Right, because of the 200 OK problem, it might have seen an empty folder and just assumed that was the input.
Exactly. So the receipt must explicitly state the exact file path it read, the cryptographic hash of the data it ingested, and the exact prompt it was injected with. We need to cryptographically prove the starting state of the agent's reality.
Got it. Question 2.
Second, under whose authority did it act? Autonomous agents don't just spawn out of the ether. Something triggered them. Was this task scheduled by an automated cron job running on a server? Was it triggered manually by a human user clicking a button in a portal? Which specific API key or credential was used to authorize the agent's existence and access in this specific moment? Accountability requires knowing exactly who or what pushed the first domino in the chain.
Just to clarify, a cron job is basically just a time-based job scheduler in computer operating systems, right? Just a clock that says, run this script at 5 p.m.
Correct. And we need to know if the clock started the job or if a human started it, because the security implications are vastly different.
Makes sense. Question 3.
Third, what side effect occurred, if any? Did the agent just passively read data to generate a summary, or did it write data? Did it move a file from one folder to another?
Did it spend money?
Did it send an email to a client? Did it change a configuration setting on a firewall? Every single interaction with the external world must be cataloged in the receipt.
Okay, question 4.
Fourth, what evidence proves the result? This ties directly back to our discussion on provenance. We cannot accept an agent simply saying, I successfully updated the customer database.
That is just a 200 OK.
Right. We need the specific row ID in the database that was changed. We need the exact artifact paths. If the agent generated an image, we need the URI, the Uniform Resource Identifier, the exact web address or local path of that image.
So we can verify it independently.
Yes, we need external receipts that a secondary, completely separate system can verify without ever having to ask the agent for its opinion again.
And finally, question 5.
Fifth, who approves the next irreversible step? This is the human purpose we discussed earlier with the new Stack article. The agent might have done all this complex work autonomously. It might have gathered the data, committed to production before the company's money is irreversibly spent or the new code is pushed live to users whose explicit, cryptographically signed gate must be passed.
Okay, I have to push back on this heavily. Because as I listen to this 5-question checklist, my immediate thought as a developer is, aren't we just recreating digital bureaucracy?
I hear that a lot.
If we require all this provenance, all these hashes, all these explicit authorizations, URIs, and row IDs for every single micro-action an agent takes, couldn't this just turn into an absolute nightmare of digital paperwork?
It's a valid concern.
The whole point of AI agents is that they are fast, autonomous, and can think on their feet. If they have to fill out a bureaucratic form in triplicate for every thought they have, we lose all the speed.
That is a very valid operational concern, and it is the primary reason developers resist building these controls. And you are right, provenance without concise interpretation is just paperwork. It becomes noise.
Yeah.
If a human engineer has to manually read a massive JSON file, a highly structured text document full of hundreds of cryptographic hashes and timestamps, for every single action an agent takes, the system will grind to an absolute halt. The human becomes the bottleneck.
But even if it's not a human reading it, even if we make it machine-readable, parsing giant JSON files takes compute. It takes processing time. Aren't we just moving the bottleneck from the human staring at a screen to the verification script chugging through megabytes of receipt data? We are slowing the machine down.
It does require compute, yes, but the key is where you place that computational burden. The solution is that the receipt must be highly actionable, and the verification happens at the boundary, not continuously throughout the interior process.
What do you mean by the interior process?
The goal is to allow the machine to move incredibly fast inside the defined perimeter. Inside the blast radius, the agent can iterate, try tools, fail, retry, hallucinate, correct itself, and synthesize at lightning speed. It doesn't need a receipt for every internal thought.
Okay, I see.
But the receipt forces the irreversible edge the moment the agent tries to cross the boundary into production or touch a real system to be slow enough and documented enough for a deterministic gate to parse it.
So to use an analogy, it's like a hyper-efficient, fully automated factory. Inside the factory walls, the robots are moving at blinding speed, building things, testing things, dropping things, starting over. It's chaotic, rapid iteration.
Exactly.
We don't demand paperwork for every bolt a robot turns, but before a finished product is allowed to be loaded onto a truck and leave the factory floor to go to a customer, it hits a very strict, very rigid, automated quality control gate. At that gate, all the telemetry of how it was built is instantly validated, and if it fails, it doesn't leave the building.
That's exactly it. The interior process can be entirely fluid, probabilistic, and fast. But the boundary, the settlement layer, must be absolute, rigid, and verifiable. The bureaucracy only exists at the perimeter where risk is transferred.
And that is exactly how we solve the 200 OK problem.
Yes. We stop trusting the transport layer or the agent's internal confidence to tell us about the outcome layer. We demand proof at the exit door.
As we bring this deep dive back to your own workflows, to the specific systems, pipelines, and agents you are building, monitoring, or managing right now, the central takeaway is incredibly clear. The future of AI agents isn't going to be defined by how confidently a model can speak, or how well it mimics human certainty, or how many complex skills it can string together in a chat interface.
Not at all.
It is entirely about how our systems remain accountable, observable, and strictly contained while those models act autonomously. The standard we have to hold ourselves to and the standard we have to demand from the tools we use must be incredibly strict. No green status without a verified physical outcome, and no handoff across a trust boundary without a cryptographic provenance receipt.
And as you think about how to implement these boundaries in your own architecture, I want to leave you with one final provocative thought to ponder, drawn directly from the complexities we've unpacked today.
Let's hear it.
Think about the moment an autonomous agent, operating inside its blast radius, discovers a new tool or a new API endpoint on its own, completely dynamically, versus a tool it was explicitly given by a developer in its initial prompt. How does the required proof of authority change when the agent is the one actively expanding its own operational boundary?
What is the smallest receipt you require before an agent may trigger the next irreversible action? Private QC only, no publication or delivery.